Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. In the immediate aftermath of the Second World War, theoretical physics found itself in a peculiar and deeply unsettling position. The discipline had demonstrated its terrifying power at Hiroshima and Nagasaki, a culmination of 4 decades of revolutionary discovery that had dismantled the placid deterministic universe of Newton and replaced it with the strange probabilistic world of the quantum. The architects of this revolution, Bohr, Heisenberg, Schrödinger, Dirac, had constructed a theoretical edifice, quantum mechanics, of unparalleled predictive accuracy for the atomic realm. Yet, as the world entered a fragile peace, the very theory that should have been physics' crowning glory, quantum electrodynamics or QED, was teetering on the brink of collapse. QED was meant to be the grand synthesis, the theory that married quantum mechanics with Einstein's special relativity to describe how light and matter interact. It was the theory of electrons and photons, the fundamental constituents of almost everything we see and touch. On the surface, its equations, formulated by the brilliant Paul Dirac, were models of elegance. The trouble began when physicists attempted to use them. When calculating even the most basic interactions, such as an electron emitting and reabsorbing a photon, the theory yielded answers that were patently absurd. The calculations produced infinite values for an electron's mass, its charge, and the probabilities of interactions. Physics had run into a wall of infinities, a mathematical pathology that signaled a profound sickness at the heart of its most fundamental theory. The methods that had triumphed at the atomic level were failing, and a generation of physicists, armed with the most powerful mathematics of their day, found themselves staring into a conceptual abyss. Into this environment of high-stakes intellectual crisis stepped a figure of singular character and intellect, Richard Feynman. Fresh from his work on the Manhattan Project at Los Alamos, Feynman was a product of a different intellectual tradition. He was born in Queens, raised in Far Rockaway, and educated at the Massachusetts Institute of Technology. His mind was forged less in the abstract, formalist crucibles of Göttingen and Copenhagen, and more in the basement workshops and engineering labs of his youth. From an early age he exhibited an irrepressible curiosity, a compulsion to take things apart, to understand their workings from the inside out. He fixed radios, built burglar alarms, and developed a deep intuitive feel for the way the world works. A physical intuition that would become the hallmark of his entire scientific career. This was a physicist who seemed to feel the physics in his bones, who demanded a picture, a mechanism for every abstract equation. His time at MIT and later as a graduate student at Princeton under the guidance of the visionary John Archibald Wheeler only sharpened this innate disposition. While his contemporaries were mastering the arcane and highly abstract operator algebra of quantum field theory, Feynman was developing his own idiosyncratic methods. He filled notebooks with strange diagrams and novel calculational tricks, seeking a direct visceral connection to the physical reality behind the symbols. His famous exploits, the bongo playing, the safe cracking, the relentless showmanship, were external manifestations of an internal intellectual style. It was a style that prized cleverness, directness, and a playful defiance of established authority, whether it was the authority of a military general or the hallowed formalism of quantum mechanics itself. It was at Princeton for his doctoral dissertation that Feynman laid the conceptual groundwork for his later triumphs. The problem that captivated him was a deep and seemingly unbridgeable chasm between classical and quantum physics. In classical mechanics, there existed a sublime and powerful idea known as the principle of least action. This principle states that the path a physical system takes through space-time, for instance a ball thrown through the air or a planet orbiting the sun, is the one for which a specific quantity, the action, is minimized. Nature, in its classical guise, appeared remarkably economical, always choosing the most efficient route. Quantum mechanics, however, described a world of probabilities and uncertainties. A particle like an electron possessed no single, well-defined trajectory. How could one reconcile the elegant determinism of the principle of least action with the inherent fuzziness of the quantum world? Wheeler posed a version of this question to his brilliant student, and Feynman's response would ultimately constitute a third, revolutionary formulation of quantum mechanics. He began by reconsidering the very meaning of a particle's path. In the standard view, a particle's state evolves from one moment to the next, governed by the local differential Schrödinger equation. Feynman's imagination took a different route. He proposed a global perspective. To calculate the probability of a particle traveling from a starting point A to an endpoint B, one had to consider every conceivable path connecting them. This was a radical and almost fantastical proposal. The particle explores all possible histories. It travels in a straight line. It takes a wildly circuitous looping trajectory. It sips back and forth, momentarily traveling backward in time. Every imaginable path, however bizarre, contributes to the final outcome. Each of these paths is assigned a complex number, a quantum mechanical amplitude, whose magnitude is the same for all paths, but whose phase is determined by the classical action calculated for that specific trajectory. The total probability amplitude for the particle to arrive at point B is then found by performing a grand summation, or more precisely a functional integral, over all these infinite possible paths. The genius of this sum over histories, or as it is now known, the path integral formulation, lies in how it recovers the familiar classical world. The phase of each path's contribution rotates like the hand of a clock. For paths that deviate significantly from the classical path of least action, their phases vary wildly from one path to the next. When summed together, these contributions interfere destructively, their effects largely cancelling each other out. However, for paths in the immediate vicinity of the classical one, the path of least action, the action changes very little. Their phases are nearly aligned. They interfere constructively, reinforcing one another and producing the overwhelming probability that the particle will be found traveling along this classical trajectory. The orderly economical world of Newton emerges as a magnificent consequence of an underlying quantum democracy of all possible realities. Mathematically, this insight is expressed in a beautiful and compact form. The amplitude to go from an initial state to a final state is proportional to the integral over all paths of the exponential of the quantity. The imaginary unit I divided by the reduced Planck constant h bar, all multiplied by the classical action s for that path. This expression, the Feynman path integral, connects the quantum amplitude directly to the classical action, bridging the conceptual gap that had puzzled physicists for decades. This work, completed in 1942, was a profound intellectual achievement. It offered a completely new way of thinking about quantum mechanics, one rooted in the Lagrangian framework of classical physics and possessing a powerful intuitive appeal. It recast the theory from a step-by-step evolution in time to a holistic consideration of all space-time histories at once. Initially, however, its reception was muted. The mathematical formalism of functional integration was unfamiliar to most physicists, and its practical utility for solving standard problems was unclear. The war intervened, and Feynman's thesis, along with its author, was swept into the urgent pragmatic work at Los Alamos. Yet this unique formulation, born from a desire to reconcile classical elegance with quantum strangeness, was the key Feynman had unknowingly forged for himself. This powerful conceptual lens, the ability to visualize quantum processes as a summation of all possible happenings, would prove to be the perfect instrument for dissecting the monstrous infinities of quantum electrodynamics. The path integral provided the intellectual foundation upon which he would soon build a new, intuitive calculus for the quantum world, one that would transform the landscape of theoretical physics and finally tame the infinite. The intellectual framework of the path integral, with its holistic consideration of all space-time histories, awaited its grand challenge. As the world emerged from the shadow of global conflict, Feynman directed this powerful conceptual lens toward the most formidable and vexing problem in fundamental physics, the quantum theory of electromagnetism. Known as quantum electrodynamics, or QED, it was a theory of sublime ambition, seeking to merge the principles of special relativity with the strange dictates of quantum mechanics. In its abstract formulation, it was a monumental achievement. In practice, however, the theory was crippled. When physicists attempted to use its equations to calculate the outcomes of even the most elementary interactions, the theoretical apparatus faltered catastrophically, yielding answers that were infinite and therefore physically meaningless. The crisis stemmed from the quantum world's inherent restlessness. According to QED, the vacuum is a seething cauldron of virtual particles. An electron, traveling through this space, is perpetually engaged in a complex dance, emitting and reabsorbing virtual photons. This process of self-interaction, when translated into the mathematical language of the theory, created divergent integrals. The calculated correction to the electron's intrinsic mass, for instance, became infinite. Its electric charge likewise ballooned to an impossible value. The theory, beautiful in its conception, seemed to predict that its own fundamental constants were nonsensical. The pioneers of the field, including Paul Dirac and Wolfgang Pauli, had wrestled with these infinities using a dense and profoundly difficult mathematical formalism. Their methods required heroic feats of calculation that obscured any clear physical picture, leaving the community with a sense of deep intellectual dissatisfaction and a theory that was functionally broken for precision work. Physics seemed to have reached an impasse, armed with equations that described the world with breathtaking accuracy at one level, while producing complete gibberish at the next. Into this perplexing state of affairs, Feynman introduced his profoundly different perspective. He began by applying the path integral formulation, originally conceived for a single particle, to the quantum fields themselves. The question became a summation over all possible configurations of the electromagnetic field through which an electron could travel. This shift in viewpoint was the first crucial step. It laid a new foundation for thinking about quantum interactions, one grounded in a summation of possibilities rather than the evolution of a single state vector through time via a Hamiltonian operator. This approach contained within it the seeds of a radically new computational method, one that would make the labyrinthine mathematics of field theory visually and intuitively accessible. From this foundation grew his most celebrated innovation, the Feynman diagrams. These were simple schematic pictures that depicted the interactions of particles. A straight line represented an electron moving from one point in spacetime to another. A wiggly line represented a photon, the quantum of light. A point where these lines met, a vertex, signified an interaction, an electron absorbing or emitting a photon. The genius of this invention was its dual nature. These diagrams were a visual shorthand for the physical processes, and they were simultaneously a rigorous and complete computational calculus. Each element of a diagram corresponded directly to a precise mathematical term in the complex perturbation series derived from the path integral. The straight line for an electron corresponded to its propagator, a mathematical function describing its journey. The wiggly line for a photon corresponded to its own propagator. The vertex corresponded to a coupling constant, a number representing the fundamental strength of the electromagnetic interaction. To calculate the probability of a given event, such as two electrons scattering off one another, a physicist could now draw all the possible ways the interaction could occur, order by order of complexity. The simplest diagram would show the two electrons exchanging a single virtual photon. More complex diagrams would include electrons emitting and reabsorbing their own virtual photons, or photons momentarily splitting into virtual electron-positron pairs. One would then follow a set of simple rules, the Feynman rules, to translate each diagram into a mathematical expression. The sum of these expressions for all relevant diagrams would yield the answer. The overwhelming complexity of the older formalisms was replaced by a systematic graphical procedure. The calculations remained immensely challenging, but they became organized, manageable, and most importantly, physically transparent. This newfound transparency was the key to resolving the crisis of infinities. The troublesome, divergent terms in the calculations appeared in diagrams containing closed loops, which represent virtual particles that are created and annihilated during an intermediate stage of an interaction. Feynman's method allowed physicists to see precisely where and how these infinities arose. The technique for handling them, known as renormalization, became physically intuitive. The infinite contribution from a loop diagram modifying an electron's path could be understood as a correction to the electron's bare mass. This infinite correction could be systematically cancelled by postulating an infinite bare mass to begin with, such that the combination of the two resulted in the finite experimentally measured mass of the electron we observe in the laboratory. The same procedure worked for the electric charge. The infinities, rather than being errors, were reinterpreted as necessary components of the calculation that were absorbed into the redefinition of a few fundamental physical constants. The impact of this work was immediate and transformative. Working independently, Julian Schwinger and Shinichiro Tominaga had developed their own more formal mathematical methods to achieve the same result, and the three would share the Nobel Prize in Physics in 1965 for their collective triumph. It was Feynman's diagrammatic approach, however, that captured the imagination of the physics community. Its intuitive power and computational efficiency were undeniable. The diagrams became the universal language of particle physics, an indispensable tool for students and researchers alike, used to this day to calculate interaction cross-sections at particle accelerators and to explore the frontiers of the Standard Model. Quantum electrodynamics, once a beautiful but crippled theory, was now a complete and astonishingly predictive science. Its predictions for quantities like the magnetic moment of the electron have been verified by experiment to an accuracy of 1 part in a trillion, making it the most successful theory in the history of science. This triumph was a testament to a unique mind that could perceive a new path through a thicket of infinities, transforming abstract mathematical torment into a simple set of drawings. The success in taming the quantum field demonstrated the profound generality of his methods, suggesting that this way of thinking, this summation over all possibilities, could illuminate other deep physical mysteries, from the behavior of interacting particles to the strange quantum phenomena found within bulk matter. Among the strangest of these quantum phenomena, a puzzle that captivated physicists in the mid-20th century, was the bizarre behavior of liquid helium. When cooled to a temperature of approximately 2 degrees above absolute zero, this otherwise unremarkable element undergoes a phase transition into a state known as helium-2. In this state, it becomes a superfluid, a liquid with the astonishing property of flowing with zero viscosity. It can creep up the walls of its container in a thin film, seemingly defying gravity, and pass through impossibly small capillaries that would block any ordinary fluid. This was a macroscopic manifestation of quantum mechanics, a collective quantum state of matter visible to the naked eye. The prevailing theoretical explanation came from the brilliant Soviet physicist Lev Landau, who in the 1940s developed a powerful phenomenological theory. Landau conceived of the superfluid as a quiet quantum vacuum, a background against which elementary excitations or quasi-particles could move. He posited two types of these excitations, phonons, which are quantized sound waves, and a more enigmatic type he called rotons, which possess a specific momentum and an energy gap. By treating the liquid as a gas of these weakly interacting quasi-particles, Landau could successfully account for its thermodynamic properties, including its specific heat. His theory was a masterpiece of physical intuition, yet it remained a description of what happens, a brilliant curve fit to the universe, offering a limited explanation for why. The fundamental connection between these hypothetical quasi-particles and the actual, jostling, strongly interacting helium atoms was missing. The challenge was to build a bridge from the microscopic world of individual atoms, governed by the Schrödinger equation, to the macroscopic world of Landau's phonons and rotons. This was precisely the kind of problem that appealed to Richard Feynman's sensibilities. It was a deep fundamental question rooted in physical reality, and the existing theoretical tools were proving inadequate. The standard methods of quantum mechanics, like perturbation theory, which had failed so spectacularly in quantum electrodynamics, were equally helpless here. The interactions between helium atoms are strong. They can be approximated as tiny hard spheres, and their jostling in the dense liquid is a complex, many-body problem of the highest order. A perturbative approach, which treats interactions as small corrections, was doomed from the start. Feynman's insight was to realize that his path integral formulation, the very tool he had crafted for quantum field theory, was perfectly suited for this condensed matter problem. The path integral asks one to sum over all possible histories or paths a system can take. For a single electron moving from point A to point B, this means considering every conceivable trajectory. For a liquid of n helium atoms, the concept generalizes. The system is the entire collection of atoms, and a path is a complete history of every atom's motion through space and time. The task was to calculate the quantum mechanical amplitude for the entire fluid to transition from one configuration of atoms to another. He began by considering the ground state of the liquid, its state of lowest possible energy at absolute zero. What would the wave function for this state look like? With his profound physical intuition, Feynman argued that since the helium atoms repel each other strongly at short distances, the wave function must be small whenever any two atoms get too close. Conversely, the wave function should be large and relatively constant for all other configurations. This simple, elegant ansatz for the ground state wave function already contained the seeds of superfluidity. From there he considered the excited states. An excitation, like a phonon, corresponds to a collective motion of the atoms. Feynman imagined creating an excitation by acting on the ground state with a density operator, essentially giving the fluid a gentle squeeze at a certain location and observing how the ripple propagates. In the language of his path integral, he was calculating the wave function for a state with a single quasi-particle of a given momentum. The resulting mathematical form for the excitation energy as a function of its momentum was a triumph. At low moment A, his derived formula perfectly reproduced the linear relationship characteristic of phonons, where energy is proportional to momentum. At higher moment A, The curve developed a distinct minimum, a dip in energy at a specific value of momentum. This was Landau's roton, emerging directly from the microscopic theory of interacting atoms. Feynman had derived the entire energy spectrum of the quasi-particles from first principles. His work also provided a beautiful, intuitive explanation for the difference between the two stable isotopes of helium. Helium-4, the common isotope, has a nucleus containing 2 protons and 2 neutrons. Its total spin is 0, making it a boson. Helium-3, a rarer isotope with 1 fewer neutron, has a half-integer spin, making it a fermion. This distinction is paramount. Bosons, according to the principles of quantum statistics, are sociable particles. They are happy to occupy the same quantum state. As liquid helium-4 is cooled, its atoms can all condense into the single collective ground state that Feynman had described. This macroscopic occupation of a single quantum state is the very essence of superfluidity. The atoms move in a coherent, correlated fashion, producing a frictionless flow. Fermions, like helium-3, are governed by the Pauli exclusion principle. They are staunch individualists, forbidden from occupying the same quantum state. Consequently, liquid helium-3 atoms cannot all collapse into a single ground state in the same manner. Each must find its own energetic niche. This prevents the formation of the simple, coherent superfluid state seen in helium-4 at those temperatures. Feynman's theory, rooted in the fundamental statistics of the constituent particles, explained with perfect clarity why one liquid becomes a superfluid and its sibling, differing by a single neutron, behaves as a normal viscous fluid. It was a stunning demonstration of the power of quantum mechanics to explain the tangible properties of matter. This foray into condensed matter physics showcased the extraordinary breadth of Feynman's intellect. The same conceptual machinery, the summation over histories, that had tamed the infinities of quantum electrodynamics, was now explaining why a liquid could climb walls. It revealed his approach as a universal way of thinking about quantum systems, a method whose power was derived from its direct physical interpretation. He had taken Landau's abstract quasi-particles and given them a concrete physical basis in the collective dance of atoms. This work solidified his standing as a physicist who could descend from the ethereal heights of quantum fields and particle creation to grapple with the tangible, messy, and equally profound mysteries found within a flask of cold liquid. His solution was a bridge between two worlds, the microscopic and the macroscopic, and it set the stage for a deeper, unified understanding of collective quantum phenomena that continues to shape physics today. Having illuminated the quantum behavior of bulk matter, his focus would soon be drawn back to the world of fundamental particles, where a new crisis of symmetry was brewing in the domain of the weak nuclear force. The intellectual calm, following his elucidation of superfluidity, proved ephemeral. A storm was gathering in particle physics, centered on a force of profound subtlety and apparent caprice, the weak nuclear interaction. Here, a foundational assumption of the physical world was about to crumble, creating the very kind of theoretical disarray that so often attracted Feynman's clarifying intellect. The world of fundamental particles, which he had helped tame with quantum electrodynamics, was once again showing its capacity for profound surprise, demanding a new chapter of theoretical insight. The crisis began with a seemingly esoteric observation known as the tau-theta puzzle. In the particle accelerators of the early 1950s, physicists were discovering a menagerie of new, unstable particles. Among them were two mesons, dubbed the tau and the theta. In every measurable respect, mass, charge, lifetime, they appeared to be the very same particle. Yet they exhibited a baffling difference in their decay patterns. The theta meson decayed into two pions, a final state with positive parity. The Tau Mason, conversely, decayed into 3 pions, a final state with negative parity. Parity, in essence, is the principle of mirror symmetry. It asserts that the laws of physics should remain identical for a system and for its mirror image. For decades, this symmetry was held as an inviolable law of nature, on par with the conservation of energy and momentum. The tau-theta puzzle presented an impossible choice. Either 2 distinct particles existed with miraculously identical properties, or a fundamental symmetry of the universe was being violated by the weak force, the very interaction responsible for their decay. The theoretical community was thrown into a state of deep consternation. To abandon parity conservation felt like abandoning a piece of physical intuition that had served science for centuries. In 1956, the theorists Sung-Dao Lee and Chen-Ning Yang took the courageous step of surveying the experimental literature. They made the stunning discovery that while parity conservation had been rigorously tested in electromagnetism and the strong nuclear force, its validity in weak interactions had been assumed without any direct experimental proof. They proposed a series of experiments to test this assumption directly. The decisive experiment was conducted later that year by Qian-Xiong Wu and her collaborators at the National Bureau of Standards. The experiment was a masterpiece of precision. It involved aligning the spins of radioactive cobalt-60 nuclei in a strong magnetic field at cryogenic temperatures. The weak force governs the beta decay of these nuclei, a process where a neutron transforms into a proton, emitting an electron and an anti-neutrino. Wu's team observed the direction in which the electrons were emitted relative to the nuclear spin. If parity were conserved, the electrons would be emitted equally in both directions, parallel and anti-parallel to the spin. The result was unequivocal. The electrons were preferentially emitted in one direction. The universe, at the level of the weak interaction, could indeed distinguish between left and right. Parity was overthrown. The experimental confirmation created a theoretical vacuum. The fall of parity meant that the existing mathematical models for the weak force were incorrect. A flurry of new theories emerged, each attempting to incorporate parity violation. These proposals were often complex, involving various combinations of 5 possible types of interaction terms: scalar, pseudoscalar, vector, axial vector, and tensor. The field became a confusing landscape of competing ideas, with experimental data offering ambiguous support for several different models. It was into this intellectual fray that Feynman, in collaboration with Murray Gell-Mann, would introduce a principle of profound and clarifying simplicity. Feynman, characteristically, was initially skeptical of the parity violation results, finding the idea aesthetically unappealing. He even made a wager against it. Upon learning of Wu's definitive results, he immediately accepted the new reality and dove into the problem. His approach, developed in parallel and in fruitful conversation with Gell-Mann, sought a single powerful organizing principle. They proposed that the mathematical form of the weak interaction current was a specific fixed combination. It was a vector current minus an axial vector current. This became known as the V-A theory. The elegance of this proposal was breathtaking. A vector quantity, like velocity, behaves as a standard arrow. An axial vector, like angular momentum, is associated with a rotation and behaves differently under mirror reflection. By postulating that the weak force couples to this V-A combination, they were building maximal parity violation directly into the fundamental structure of the theory. This specific mathematical form explained why the emitted electron in Wu's experiment had a definite handedness or helicity. It seemed the cosmos, at this fundamental level, possessed a distinct directional preference, a sort of subatomic favoritism that sent theorists scrambling to update their understanding of nature's symmetries. The V-A formulation did more than explain parity violation. It provided a unified and predictive framework that tidied the entire field of weak interactions. It correctly described the beta decay of the neutron, the decay of the muon, and a host of other weak processes with startling accuracy. Where other theories had struggled to fit the data or had required cumbersome adjustments, the V-A theory succeeded with an almost minimalist grace. It was a testament to Feynman's physical intuition, his belief that a complex set of phenomena should ultimately yield to a simple underlying law. The paper he co-authored with Gell-Mann, published in 1958, effectively settled the matter, establishing the definitive low-energy form of the weak interaction. The historical impact of this contribution is immense. The V-A theory became an essential cornerstone of what would evolve into the modern standard model of particle physics. It was the correct phenomenological description that later theorists like Sheldon Glashow, Abdus Salam, and Steven Weinberg would incorporate into their unified electro-weak theory, which describes electromagnetism and the weak force as different manifestations of a single, deeper interaction. Feynman's work provided the solid ground upon which this grander synthesis was built. He had looked at a field in chaos, beset by a fallen symmetry and a proliferation of confusing data, and with one elegant stroke of mathematical insight, imposed a lasting and beautiful order. This achievement once again highlighted the unique character of his scientific mind. He possessed an uncanny ability to distill the essential physical principle from a morass of experimental detail and competing formalisms. His work on the weak interaction provided a crucial grammar for the language of particles, a rule that governs how they transform and decay. With this piece of the puzzle firmly in place, the stage was set for physicists to probe even deeper into the structure of matter, to ask what lay inside the very protons and neutrons at the heart of the atom, a question that would occupy Feynman in the next phase of his extraordinary career. His work on the weak interaction provided a crucial grammar for the language of particles, a rule that governs how they transform and decay. With this piece of the puzzle firmly in place, the stage was set for physicists to probe even deeper into the structure of matter, to ask what lay inside the very protons and neutrons at the heart of the atom, a question that would occupy Feynman in the next phase of his extraordinary career. This inquiry would lead him from deciphering the cryptic messages emerging from new experiments to conceiving of entirely new forms of computation, demonstrating a mind equally at home, interpreting the present and architecting the future. The late 1960s presented the physics community with a profound experimental shock, originating from the powerful new machinery at the Stanford Linear Accelerator Center, or S. In a series of experiments on what became known as deep inelastic scattering, physicists fired high-energy electrons at stationary proton targets. The expectation, based on prevailing models, was that the electrons would scatter off the proton as if it were a diffuse, uniform cloud of charge. The results were startlingly different. A significant number of electrons recoiled at large angles, as if they had struck something small, hard and point-like within the proton. The data exhibited a curious property dubbed scaling, a mathematical relationship suggesting the proton's internal constituents behaved as free, independent particles during these fleeting high-energy collisions. The challenge was immense to construct a theoretical model that could account for this bizarre internal anatomy. Feynman's response to this puzzle was a masterpiece of physical intuition. While others pursued complex field-theoretic formalisms, he developed a disarmingly simple and powerful picture. He proposed that at the extreme energies of the S-SLAC experiments, the proton could be conceptualized as a loose agglomeration of point-like constituents, which he christened partons. In the reference frame of the high-energy electron, The proton is Lorentz contracted into a pancake, and the internal motions of the partons are slowed by time dilation. The interaction happens so swiftly that the partons have insufficient time to interact with one another. They behave for that brief instant as free entities. The electron scatters elastically off a single parton, and the overall experimental result is the incoherent sum of these individual collisions. This parton model was a breathtaking simplification, yet it beautifully explained the observed scaling behavior. It provided a direct, calculable framework that experimentalists could use to interpret their data. The model made concrete predictions about the distribution of momentum among the partons, allowing for a direct comparison between theory and the patterns emerging from the accelerator. Feynman's approach supplied the indispensable conceptual bridge between the raw data of scattering events and the deeper, more abstract theory of the strong force that was slowly taking shape. His partons were later identified with the quarks and gluons of quantum chromodynamics, or QCD. The very property that made his model work, the apparent freedom of the partons at high energies, found its formal explanation years later in the QCD concept of asymptotic freedom. Feynman's physical picture had anticipated the core result of a far more elaborate mathematical theory, once again affirming his conviction that a profound physical insight is the most valuable tool in a theorist's possession. This capacity to reimagine the very substance of reality extended from the infinitesimal constituents of a proton to the abstract architecture of computation itself. Having provided a lens to peer inside the atom's core, his gaze turned toward a different kind of fundamental limit, the boundary between what is computable and what is physically possible to simulate. The problem was, and remains, a deep one. Simulating the behavior of a quantum mechanical system on a classical computer, a machine built on the principles of zeros and ones, is an endeavor plagued by an insurmountable scaling problem. To describe a system of a few dozen interacting quantum particles, a classical computer must store and manipulate a list of probability amplitudes for every possible configuration of that system. This number of configurations grows exponentially with the number of particles. Adding one more particle can double the memory and processing power required. The simulation of even modestly complex molecules or quantum phenomena quickly becomes intractable for any conceivable classical supercomputer. In a landmark lecture in 1981, Feynman articulated a solution of stunning elegance and foresight. He posed a simple, profound question: if nature operates on quantum principles, what kind of computer would be best suited to simulate it? His answer reoriented the entire discussion. He proposed the construction of a computer that is itself a quantum mechanical system. A quantum computer would harness the very principles that make simulation so difficult for classical machines. Its fundamental components, which we now call qubits, would exist in superpositions of states. Its operations would manipulate these states through entanglement, the spooky interconnectedness of quantum particles. Such a device, he argued, would be a natural analog for the systems it was designed to model. The exponential growth in complexity that hobbles a classical computer becomes, in a quantum computer, an exponential growth in computational space and power. A system of n qubits can explore a space of 2 to the power of n states simultaneously. Feynman envisioned a universal quantum simulator, a controllable quantum device that could be programmed to mimic the behavior of any other quantum system of interest, from complex molecules for drug discovery to exotic states of matter. This insight transformed a fundamental limitation into a spectacular opportunity. The peculiarities of quantum mechanics were recast as a powerful computational resource. This conceptual leap is widely acknowledged as one of the seminal moments in the history of quantum information science, providing the foundational vision for a field that now promises to revolutionize medicine, materials science, and cryptography. In both the heart of the proton and the future of the computer, Feynman saw with a clarity that collapsed complexity into beautiful, functional, and world-changing ideas. This capacity to reframe fundamental limitations as powerful new paradigms extended from the invisible world of quantum computation into the tangible arenas of human learning and public accountability. The same intellectual engine that saw computational power in quantum uncertainty also saw a path to clarity through the dense thickets of established pedagogy and institutional obfuscation. Feynman's influence, therefore, radiates outward from pure theory, shaping how science is taught and how it functions as a pillar of a rational society. His most monumental contribution in this sphere is, without question, the Feynman Lectures on Physics. In the early 1960s, the California Institute of Technology faced a common pedagogical challenge. The curriculum, while rigorous, had become somewhat stale, presenting physics as a collection of solved problems and axiomatic laws. The intuitive fire, the thrill of discovery that animates the research frontier, was often lost in the translation to the undergraduate lecture hall. Feynman was tasked with revamping the introductory physics course, an assignment he undertook with characteristic intensity. The result was a 3-volume masterpiece that re-envisioned the entire structure of physics education. The lectures were a radical departure from the standard approach. They begin with the atomic hypothesis, the single most profound and generative idea in all of science, and build the edifice of physics from this foundation. Conservation laws appear early, presented as deep consequences of the symmetries of space-time, a perspective usually reserved for advanced graduate students. He weaves connections between disparate fields, thermodynamics, mechanics, electromagnetism, revealing a unified tapestry where other texts presented a patchwork of separate domains. His voice, transcribed almost verbatim, is conversational, inquisitive, and relentlessly focused on physical intuition. The mathematics serves the physics. The equations are tools to sharpen understanding, expressions of physical reality. He wanted students to see the world as a physicist sees it, to feel the push and pull of forces, to visualize the dance of fields and particles. The enduring power of the lectures lies in this philosophical stance. While perhaps too conceptually demanding for some first-year students, seeking simple problem-solving recipes, they became a source of profound inspiration for generations of physicists, a text to be returned to again and again for a fresh jolt of insight. They represent a complete system of thought, an invitation to reconstruct one's own understanding of the universe from first principles. Decades later, this same commitment to fundamental principles and unvarnished truth would be displayed on a far more public and somber stage. Following the catastrophic explosion of the Space Shuttle Challenger in January 1986, President Reagan convened the Rogers Commission to investigate the disaster. Feynman, to his own surprise and initial reluctance, was appointed to the panel. He found himself in an alien environment of Washington politics, military protocol, and NASA's carefully managed public relations. He quickly grew impatient with the formal briefings and the mountains of incomprehensible reports. The core problem, as he saw it, was a deep cultural sickness within the space agency, a disconnect between the management's rosy projections of safety and the grim realities known by the engineers on the ground. To uncover the physical truth, he bypassed the official channels. He spoke directly with the technicians and low-level engineers, the people who worked with the hardware. They told him of their concerns, particularly regarding the performance of the rubber O-ring seals in the solid rocket boosters at low temperatures. While the commission heard testimony filled with acronyms and statistical risk assessments, Feynman sought a direct physical demonstration. During a televised public hearing, he performed one of the most brilliant and devastatingly simple experiments in the history of science communication. He took a small C-clamp, compressed a piece of the O-ring material, and submerged it in a glass of ice water provided by a page. After a few moments, he removed the clamp. The rubber failed to spring back, its resiliency gone. In that moment, Feynman demonstrated for the world the fundamental physical failure at the heart of the tragedy. He had cut through layers of bureaucratic denial with a glass of water, revealing that nature's laws are absolute and indifferent to managerial directives or launch schedules. His appendix to the Commission's final report, a personal and scathing critique titled Personal Observations on the Reliability of the Shuttle, became a classic text on the pathology of institutional self-deception and the moral responsibility of the scientist. Synthesizing these varied achievements, the quantum electrodynamics, the Parton model, the vision for quantum simulation, the lectures, the O-ring demonstration, reveals a coherent and powerful intellectual signature. The ultimate Feynman legacy is a complete methodology for confronting the unknown. It is a system built upon a foundation of ferocious intellectual honesty, the absolute demand first and foremost to avoid fooling oneself. From this foundation rises a deep-seated belief in the primacy of nature. For Feynman, the experiment, the observation, the physical world itself was the supreme and final arbiter of truth. All theories, all mathematical formalisms, all elegant constructions of the human mind were provisional, beautiful perhaps, yet ultimately subservient to the verdict of reality. This belief fueled his relentless drive for intuitive, almost visceral, understanding. He needed to see how the machinery of the universe worked, to translate the abstract symbols of equations into a tangible mechanical picture. And this entire intellectual structure was wielded with a profound and unwavering disdain for unearned authority. He questioned everything and everyone, applying the same skeptical lens to a cherished principle of physics as he did to a general's testimony or a corporate press release. This unified approach, this holistic way of thinking that armed curiosity with integrity and courage, is his most powerful and enduring contribution. It offers a timeless and essential model for scientific inquiry, for public reason, and for the simple, difficult, and vital human endeavor of figuring things out.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.